Chapter 7, Atomic Structure and Periodicity. What we're referring to with periodicity is the periodic table and a certain characteristic of the periodic table that is derived from atomic structure. If you know how the periodic table is structured, you can write the electronic structure of an atom or one of its ions very easily. It's built that way. So let's get some information under our belts. What we know about the universe, as a matter of fact, much less the atoms that occupy it, is delivered to us largely by light, that information. The only time we get direct access to atoms in any other place but the Earth is if we go there. We've been to the moon, so we brought samples back from the moon and can run some non-electromagnetic radiation tests on them. We've sent probes to Mars, some comets, some of the outer planets, and they have been able to sample from those direct samples from those sources. But the information they send us back, of course, travels on a light beam. Well, what you'll notice about elements is when they're excited, as in an explosion or in a flame, they will give off certain colors. And those colors are indicators as to what the atoms are doing inside. Okay, predominantly with their electrons. If you get it hot enough to affect the nucleus, then you're talking about the sun. Right, so we're talking about electron movement in atoms. This electromagnetic radiation answers some questions. Well, actually, it poses more questions than it answers. And we want to know why we get those colors. Originally, it was just a curiosity. But as it turns out, those colors carry with them lots of information. We wonder why the different chemicals give us different colors. Sodium is characteristically an orange flame. Potassium is a little more lavender. Barium is blue, which is kind of rare, especially in fireworks. It's difficult to produce blues. Yellows are easy. Right? All you need is a little zinc, even calcium or sodium in the right combination. And it's also temperature dependent. So if you get it really hot, then you move more toward the yellow and blue end. But you still, with these, you don't get hot enough to give you a blue. It takes that element to do it. We used to have school kids come through on tours for my USDA lab. Since I ran the analytical lab, internal lab for the whole lab, I had access to some rather expensive equipment. And I would aspirate some samples with these different elements through one of my instruments, which had a hot flame in it. It was an acetylene flame. And we'd get some oohs and ahs out of these colors that would come out. So we also noticed that we get different colors from elements, chemicals, when they're in the flame versus when they're in solution. So there's some different type of chemistry going on there when you put them in solution that gives you those different colors. And not only that, there's a difference between emission and absorption colors. Okay. The emission, of course, is coming directly from the element. Absorption is there's light coming from behind the element or reflected off the element, and it's absorbing some of the wavelengths. And what's left over is what you see. That's why in the summertime, most tree leaves are green, or most plants, vascular plants are green. They have chlorophyll in them. And there's so much chlorophyll in there, it swamps out all the other colors. You only see the other colors when the leaves start to die in the fall. But chlorophyll is green because it absorbs the red end of the spectrum and the blue end of the spectrum, and what's left over is green. So that's what we see. Okay. And we wonder why some colors, some chemicals tend to, of a similar nature, tend to produce the same colors. There's another clue. How about red blood cells? Why are blood cells red? Well, there's hemoglobin, of course, in the blood cells. And each hemoglobin molecule has 4 iron atoms embedded in it. It's called chelation. Chelation comes from the Greek word that means claw. So there's like a claw of a molecule that holds the iron in there. And it turns red when oxygen is associated with it. Right? So that's why arterial blood is bright red. And venous blood is more sort of a bluish tinge. Of course, when venous blood comes spurting out, once it hits air, it picks up oxygen, turns red. But if you could look at it without that oxygen, you would see that it'd be more kind of it has sort of a bluish tinge to it. Okay, crawfish shells. I did my master's research on crawfish processing waste. We had down in Louisiana, there crawfish that we brought into plants. They'd be boiled, and then they'd have people there that would just pick them apart, pull the meat out, tail meat, and they'd freeze it and send it all over the country. You can find it just about anywhere now. But the shells, at least the Louisiana crawfish, the shells are usually red in color. And that's due to this chemical here, primarily astaxanthin. And it's the characteristic of the astaxanthin is that it has these double bonds in it. And that every other bond is double bond. These are all what we call conjugated. In other words, the electrons, it's set up so that the electrons can freely travel backwards and forwards because these bonds are all conjugated. And that affects the color that it absorbs. And just a slight change will change the color. The leaves that turn colors in the fall, a lot of those colors, not all of them, but a lot of those colors are due to these types of structures, these carotenoid pigments. And all you have to do is just change one of these double bonds in here. Say, get rid of that one, and it'll change the color completely. Okay, so let's learn about electromagnetic radiation, or light. There are 3 measurements that are associated with light. In fact, there are 3 measurements that are associated with any type of wave. That's true for sound also. Right? So once you learn this, you can apply it to sound. It's just, it'll have a different speed. Okay. And it'll have different wavelengths and frequencies. But the wavelength we designate with a small lambda. Okay. And the frequency, nowadays, they use an F, a small f, but you will also see it with a Greek letter, nu, N-U. Looks like a V. And then, of course, speed for light is c. Speed of light in a vacuum, speed of light is constant at 2.9979 times 10 to the 8th meters per second. It changes somewhat when it travels through matter, and that gives rise to refractive index, but that's not part of this course. You have to take my physics course or the physical science course to get that one. Anyway, if you know these three factors, you can describe the behavior of light, and you can identify its colors. Okay, so there are your, you can substitute a small f in here nowadays, I think. It's kosher. But what does wavelength mean? Well, wavelength is the distance between two wave crests. So when you think of light as a wave, and we typically draw it as a sine wave, which may not mean anything to you now, but it has intensity here, and this is distance, and the distance between these two positions here is a wavelength. And of course, the standard to measure in the SI system is a meter. Now you can measure this anywhere. You can measure it here to here. It has to be, if it's descending here, it has to descend here. That's why we use a crest. It's less likely to make a mistake. Now, frequency is how many waves pass a single point in a second. Right? And since a wave is not really a unit of measure, in fact, it varies so much, the number of waves or the cycles per second means that while this one might be have units of meter, this one will have units of reciprocal seconds. It's like cycles per second. But since cycles is not a real unit of measure, this is all you're left with. But in honor of one of the giants of this era, when light was being discovered, being characterized, and for his work with electromagnetic light in communications, we name this also Hertz. Now, when you get ready to do calculations, Hertz doesn't do you any good. You need to know this value right here, reciprocal seconds. And then the speed of light here is meters per second. So these all three are related to one another with this formula. And the speed of light is a constant, at least in a vacuum. And this constant is equal to wavelength times the frequency. So if wavelength is in units of meters and frequency is reciprocal seconds, obviously meters per second. I always like to do units when I see a new formula, just to see if it's kosher. Okay, so once you know this, if you know the frequency, you can calculate the wavelength, vice versa. Or if you know both of these, you can calculate the speed of light. And obviously, for any other type of wave, if you know both the frequency and the wavelength of that wave, you can calculate the speed of the wave. Okay, this is the publisher's idea of an explanation. It just says the same thing I did. Wavelength gets shorter. So as the wavelength gets shorter, if this formula is going to hold true, then if that's constant, if the wavelength gets bigger, the frequency has to get smaller. Or if the frequency gets bigger, the wavelength has to get shorter. And they're inversely proportional. And if you plotted both of these on a graph, you get a hyperbola, just like Boyle's law, PV equals constant. Okay. Inverse proportional. This is a representation of the electromagnetic spectrum. In other words, these are all the light waves that we know. Various exotic forms of radiation notwithstanding that you will see in the popular movies or TV like Star Trek. I think one time they came up with theta waves. What the hell is a theta wave? It's not on my spectrum. Anyway, one thing that jumps out at you is the visible range of wavelengths is very narrow. In other words, our eyes only respond to a very narrow band of electromagnetic radiation. And it occurs between 4 times 10 to the minus 7th meters and 7 times 10 to the minus 7th meters. Okay. Now, another frequently used unit of measure for wavelengths, which makes it more convenient to operate, is the nanometer. Right? Remember, nano means 10 to the minus 9th. So 10 to the minus 9th, if we convert meters to nanometers, this will be 700 nanometers. And that would be 400. So the visible range is between 400 and 700 nanometers. And we associate various frequencies. I should stick to wavelengths for now. Various wavelengths we associate with different colors. And I remember in grade school memorizing the colors of the rainbow. Right? Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. What we're going to learn pretty soon is that within a shortening wavelength, an increasing frequency, right, by contrast, means more energy. So the very high energy electromagnetic waves are down here, and the very low energy electromagnetic waves are up here. Okay, we got a formula for that, and I'll give it to you in a minute. But when you increase the wavelength past red, you get the infrared. And what's characteristic of matter and it's interacting with light is that sometimes matter is responsive to various wavelengths of light, and sometimes it's not. So your food is responsive to infrared radiation. So when they get it ready, they stick it up on that shelf, and it's got these red lamps over it. They're infrared, they're heat lamps. And they emit infrared radiation to keep your food warm because your food will absorb that energy. Microwaves, some molecules will absorb that energy. Water in particular at a given microwave frequency. The original, let's see, who built the original radar range? Microwave ovens. Radar range. Shoot, I used to know that. But it's based upon the fact that microwave radiation of a particular wavelength is very efficiently absorbed by water molecules. And maybe we'll talk about that maybe once, called resonance. And if you can impart that energy in the light to the molecule, it will increase its kinetic energy and get hot, and everything around it will absorb that energy too. So microwaves are effective at heating food. Now, water is not the only molecule. There are some other molecules that will absorb in that range also. I used to use that fact to digest plant material. I put concentrated acid in there with my plant material in these little Teflon cups, put the lid on it, and stick it in a pressure vessel. Just crank it down and stick it in the microwave and run it for several minutes. And then when you open it up, under a hood, of course, then you get this puff of brown smoke from the acid that's digested your material. And then there's nothing left in there but liquid, and whatever was in your plant material is dissolved in that acid. So I don't think it's just the water that's left in the acid or the plant material. I think the acid absorbed it also. Anyway, so longer and longer wavelengths, radio waves, we generally use for communication. And one reason is that they travel so far. Even FM will travel a long distance, but the AM and the shortwave radio wavelengths will travel enormous distances. They'll even go beyond the horizon. And the reason they'll go beyond the horizon is, let's see, if here's the surface of the Earth, there's radiation from the sun is ionizing the atmosphere, right? And it's the solar wind is bombarding our planet, but we've got this magnetic field that protects us, protects our atmosphere. And what it does is it sends all these charged particles out to the outside in the rarefied upper atmosphere, ionosphere. And they call it ionosphere because it forms ions up there. And these ions up here, when we broadcast a short wave, they hit that thing and it forms a reflective layer. So you can go beyond the horizon with these short waves and AM. As a kid in Tennessee, I used to pick up Chicago at night, you know, when the sun wasn't interfering with its radiation and other stronger sources weren't there. I could pick up Chicago. And even now, when I drive Logan on Friday mornings, I can't pick up anything from Beckley, right? You're down in the hollers. I'll tune in 750 from Atlanta, pick up Atlanta radio. Not very interesting, but it's something to hear in the background because they're always, again, traffic reports and weather reports, and it's nothing much about else. So I'll listen to that for a while. When I got tired of that, I'll turn on the CD. Okay, so that's the long wavelengths. Now the short wavelengths, we're starting to build up energy, more energy. The ultraviolet, right? And we, for physiological purposes, we divide ultraviolet into A's and B. Ultraviolet A and B. And the protective creams that you put on yourself are designed to absorb, preferably both of them. But one of them, I can't remember which. I think the A is more damaging than B. But be that as it may, ultraviolet radiation, we can't see any of these. But we know it's there because of its effect. And now we have instruments that can measure it. X-rays are even higher energy, right? We've used those for quite a long time to non-invasively investigate internal tissues, particularly bone. Now we can take X-rays with very, very low energy exposure because we have better detectors. Used to be, they had to give you a massive overdose of X-rays just to get the film to expose. And it was dangerous over a lifetime. If you had several of those, you would do tissue damage or develop cancer. But now they use electronic detectors, and very, very soft X-rays will go through and give them the information they want. So you can have thousands of X-rays over your entire life, and it's no worse than an airline pilot going up to 30,000 feet 3 times a week. Gamma rays, the most energetic light emissions in the universe are gamma rays. In fact, there are some sources, and I can't recall right now what the sources are that emit these, but the gamma ray bursts from other parts of our galaxy, if they're very directional. So if they're aimed at our planet, then they're powerful enough, even though they're light years away, they're powerful enough to strip the atmosphere off of our planet. So if we get a direct hit from a gamma ray burst, it's all over with. That's known as an ELE, an extinction level event. Fortunately, they're so directional that we can kind of off to one side see them happening, but they're not dangerous when we observe them. Okay, so there's your electromagnetic spectrum. And the point of this slide is just to draw the connection between the conversion of energy. Right? The conservation of energy is a law in the universe that you cannot create energy, you can't destroy energy, you can only convert it from one form to another. Kind of like the conservation of mass, right? From Lavoisier. You can transfer mass from one place to the other. You can't create it, you can't destroy it. It's always preserved in a chemical reaction. So when we add energy in the form of electricity to this pickle, right, it glows. So that must be some pretty high voltage. And not only does it produce light, but it produces lots of heat. So I wouldn't be surprised if that pickle is steaming by now.
Looks like
It's like what?
it looks like the forks are melted.
Yeah, the forks are at the very least they're corroding, right? Because pickles they have acid in them, so they probably corrode the metal, especially if it's silver. Okay, so we're still talking about light, and we're going to give you just a brief history lesson. The wave nature of light was championed by James Clerk Maxwell. His equations described light in terms of waves, and they were very effective in describing the behavior of radiation in those days. From what they knew of light, they thought, well, with Maxwell's equations, we know everything there is to know. You know, we might as well just pack up and go home. And under certain circumstances, those equations are still valid. Problem is, general relativity and quantum mechanics happened. And under certain circumstances, these equations don't work anymore. One particular phenomenon that was observed that just blew Maxwell's equations out of the water was the photoelectric effect. Couldn't explain, his equations could not explain the photoelectric effect. It took Einstein to do that. In 1905 or 06, he published that work. And around 1921, he got the Nobel Prize for it. So when things get really big or really small, just classical mechanics just break down completely. Yeah, they were wrong. There was a whole lot more to discover, which is characteristic of science. Job security. Max Planck came along around 1900, and he was interested in what we call black body radiation. And that pickle was a good example. If you heat something up to a certain temperature, it will begin to glow with a certain wavelength of light. And if you heat it up a higher temperature, it'll glow with a shift more toward the blue, and it'll keep shifting. That's how we know the temperatures of stars, because we look at the light that they emit and we treat them as a black body. In other words, as if they're not creating their own energy. They're only heated up, and the emission is based upon that. And that's fairly valid, because the energy is being generated inside the star where you can't see it. So by the time you see it, it's up here in the star's atmosphere, exciting those molecules, and you can determine the temperature of the surface of the star with this information. One other thing that Planck discovered was that matter, particularly atoms, gain and release energy in packets, in defined amounts. And he even came up with this equation. And that's that little v that it's actually the Greek letter nu. This is a constant, Planck's constant, times the frequency. And that's equal to the energy of that packet. So notice that the energy of the packet increases with the frequency. So with high frequency, like the gamma rays, very high frequency, very high energy for each one of those packets. We call them photons. Right. Now, I'm not sure how you get a photon you can deliver a photon in a torpedo, but Star Trek did it somehow or other. This is called quantized energy. In other words, quantum refers to fixed whole number amounts. So you can only have this amount, and if you have more, you've got to have the next quantum and the next quantum. Nothing in between. It's not continuous. Maxwell's equations assumed that radiation was continuous from one end to the other, energy-wise, wavelength-wise. And that was a natural assumption based upon what they knew of light in those days. So what this leads to is the duality of light. In other words, under certain circumstances, you can treat light as if it's a wave, right? And Maxwell's equations work fine. Under other circumstances, you have to view light as a particle. And this is one of those situations. It behaves like a particle. I mean, it's individual packet traveling from here to there. So that leads us to that age-old dilemma. Is light a wave or is it a particle? Well, the answer to that is yes. It's both. Okay. So using Planck's equation, energy of the photon equals h nu, we can also, if we don't know the frequency, then we also have this equation we can fall back on. Right? We can calculate the frequency and then plug it in the equation, or we just solve for the frequency. Right? And then just plug it in the equation here. And you've got a new equation where you can do the calculation in one step. This is Planck's constant right here. And you don't have to memorize it. That's going to be in useful information. But it's like any equation in math and science. The really important work is recognizing the relationship between energy and frequency. Once you've got that relationship where you say this is proportional to that, then all you need is a proportionality constant, we call it. Something that make the units, these units are in joules, and these units are in reciprocal seconds. That's that. Right? So you need a proportionality constant to make this into an equal sign. So your proportionality constant has to be joule seconds. So when you multiply it by hertz or reciprocal seconds, seconds cancel, you're left with joules. That happens all the time in math and science. The real important work is recognizing the relationship. And then not insignificant work is figuring out what those values are. Okay. Oh, photoelectric effect. I got a video.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also— What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
The interesting part of that discussion for me was the tail end, when Robert Millikan came in. Einstein did the theoretical work for the photoelectric effect, developed the set of equations that describe it. And then Millikan came along and proved it. He didn't plan on proving it, but his experiments did prove it. And you'll recall Millikan is the one who determined the mass of the electron with his oil drop experiment. So that wasn't the only thing he did with his time. And who's to say that he did busy work himself? He probably had graduate students do it for him. So what does the photoelectric effect have to do with the quantum nature of light? Well, these are observations. When, and usually we observe this with metal, but not necessarily. If you have a metal here, and light is impinging on the surface, then electrons will only be emitted by a certain frequency of light or anything with a shorter wavelength or a higher frequency. So what that means is there's a minimum amount of energy that's required to eject an electron. And it has to be supplied by this equation for that light. And it's characteristic of the metal. So sodium would have a certain amount of energy required. Zinc would have a different amount, probably more. And other metals, they have characteristic amounts of energy required to eject the electron. The minimum amount of energy. That's called the work function. certain amount of work has to be performed to kick that electron off. Now, at that minimum amount of energy, this electron is emitted with no kinetic energy of its own. It's just freed from the surface. And from then on, if you want to collect it, you've got to provide a positive attractor to get it over there. But if you exceed the amount of energy required for the work function, then the leftover energy is converted into kinetic energy. Okay? So that means the amount of energy coming in, the actual amount of energy coming in, carried by the wave, is equal to the work function plus the kinetic energy of the electron. So you can account for all the energy that's coming in on that wave. This is only the minimum. That's the minimum. And then that's the excess. So the total accounts for all the energy that's contained in that wave, that light wave. Okay, so this threshold frequency must be met in order for an electron to be ejected. And like I said, no electrons will be emitted for a longer wavelength. It doesn't matter how intense the light is, right? How much energy, we call it flux. How much energy is passing a certain point for every second? Doesn't matter. If the photon energy is not sufficient, then no electron will be ejected. Doesn't matter how many photons you throw at it. But once you reach that work function energy, once you've exceeded it, then if you intensify the light, more electrons will be emitted because you have more photons impacting the surface. Right. Okay. So in terms of electricity, that's called current. So you can increase the current by the intensity once you've met the minimum amount of energy required with your light. Okay, and this is the kinetic energy discussion. And if you increase the frequency, you increase the kinetic energy beyond the work function. In fact, my physical science survey class, I think they're in the middle of it now. They're doing a lab, a virtual lab on photoelectric effect. And it spins their heads around, obviously, because it's not a physical science survey is not a course that science majors take. These are primarily education majors, but I hit them with it anyway. Just see how well they do. Some of them gobble it down and chew it up. They're good at it. Some of them not so good. So what are the conclusions? This electromagnetic radiation, the light, arrives at the surface of the metal in discrete packets or photons. It behaves as a particle. And each quantum of light, each photon, possesses a minimum amount of energy needed to excite the electron, if it's of the right frequency. What happens if the photon doesn't have enough energy, right? It could be one of two things. It could be reflected from the surface, right? If it was polished to a very fine surface, it could be reflected off the surface, or it could be absorbed by the metal without ejecting an electron. And if it's absorbed, that means it adds to the heat of the metal. So that's why they call them thermal photons. If they can't make the minimum, the work function, then they have the potential to add heat to the surface. And like I said before, any excess energy is converted into kinetic energy for the electron. Now, where do these electrons come from? Well, they come from the metal. Right? Metal's got electrons around each atom, and the outermost electrons are the closest to outer space. In other words, they're the ones that receive the energy, and it takes the least amount of energy to eject those outer electrons. So I would expect, I don't know this to be a case, but I would expect that those electrons that are furthest from the nucleus, say down here, metals, they might have the lowest energy work function because their electrons are way, way far away. And they're effectively shielded from the nucleus. So it should take a small amount of energy to get them off and shift it more toward the red. So what's intensity? Well, intensity is actually a measure of photon density. That is, intensity just means you're throwing more photons at the metal surface. Okay. So what does this effect tell us about the structure of an atom? Well, the interaction of light and matter occurs with its electrons. That's where the business happens. Light and electrons interact. Right? That's the first statement that first conclusion we can draw from this effect. Also, that this photon of a certain energy is specifically tuned to the movement of an electron from one energy level to a higher energy level. There are no in-betweens. In other words, so that tells us that the electrons surrounding an atom are not just flying around willy-nilly anywhere they want to go. They are confined to certain energy levels around that atom. Now, when an electron is promoted to, I just had a flashback on a movie, sorry. I was thinking of Chronicles of Riddick, where they were talking about promoting the Lord Marshal from half dead to full dead. So we're promoting these electrons to infinity. That's what you're doing when you eject an electron from an atom, providing enough energy to eject it from the influence of that atom itself. Okay. Got any more conclusions? Well, we know that this is true. Any excess energy is converted into kinetic energy, right? And if we can apply kinetic energy to an electron movement, then we can imply that the photon has mass. Based upon conservation of momentum. In any collision, momentum is conserved. Okay. So Einstein didn't stop there. Soon after, in fact, 1905 was a very productive year for this guy. He was young, had lots of time on his hand, reviewing patents at the patent office in Bern, Switzerland. He'd get his patent work done in a couple of hours, and he'd spend the rest of the day just daydreaming, working on his theories. So he wasn't attached to any universities. He just sent his articles in to whatever publisher would accept them, and they were published. And he came up, first of all, with his special theory of relativity. And what this did, among other things, was prove that light has mass. Now, this is not rest mass. Light has mass because it's moving at very high speed. We call that relativistic mass. Rest mass would be like me, like 205 pounds. But anything moving very fast has a different kind of mass, which is attributed not just to its intrinsic characteristics, but to how fast it's moving. This is why they say that we'll never exceed the speed of light if we just use simple impulse engines. Because the faster you go, the higher your relativistic mass, and then the amount of energy required just goes like that. Okay, so he came up with this equation that equated light, that combined, I should say, light, mass, and energy. So this light is a constant. So mass can vary, and if mass increases, energy increases. But it increases by a massively huge amount, simply because we're squaring light. We're squaring the speed of light. So a small amount of mass converted to energy is huge. Okay. This theory of relativity was confirmed in 1922 experimentally by Arthur Compton. I'm trying to recall what experiment he performed. I think he's the one. Now, I better keep my mouth shut right now because I'll do more confusing than I explain it. So let's move on. So it's not just a theory with no basis in fact. It has been proven experimentally. So nature both has a wave and particulate properties. It's both a wave and particle. Both are correct. Okay. Characteristics of a wave. Okay. When you know you have a wave, you're going to see diffraction. So diffraction occurs when wave encounters an edge. It could be at the edge of a like this, like when the wave comes in like that. This serves as a point source. So at this point source, it starts to make its own waves like that. Right? If wave behaved only as a particle in these circumstances, the particles would go like this, and it would be black down here and light up here. Very sharply defined, but it's not. You get some light showing over here. And this is an illustration of how it spreads. This serves as a point source, and we get a new wave formed right here. Now, if you also, this diffraction, if we put another slit over here, then these two waves that are formed from that point, those 2 point sources, will interfere with one another. And if we put a detector out here, a film or a series of diodes, you'll see light and dark bands, because the interference will either enhance or cancel. And you'll see those bands spread out here. The strongest one will be right in the middle, and then you'll have lighter ones as you go out. That's diffraction. Refraction is the bending of light as it passes through a transparent medium. And that has to do with its speed. When it encounters, say, glass, a light beam will slow down. So, and that can only be explained by wave characteristics. So if the wave passes through, this is our transparent medium. If the wave is coming here like this, right, this part of the wave hits it first. It slows down. So it's kind of like the Charlton Heston chariot race. Right? He has one horse on the inside that's very stable. Right? So when he hits that turn, it tends to slows down and it drags the wave like this. So now when the wave eventually enters here, it might still be like this, but eventually it changes direction. So if that's the direction, now this is the direction. That's refraction. And we use that in lenses. And it's due to the wave nature of light. Particle nature of light, best example of that is photoelectric effect. Wave nature cannot explain photoelectric effect. Or if it tries to explain it, it explains it wrong. Because the wave nature of light says that when you increase the intensity, you're going to reach a point where you will start ejecting electrons. Okay. Now, let's start digging into the atom using what we know about light. There are several sources of light, some natural, some man-made, that produce what we call a continuous spectrum. That is, it has all the colors of the rainbow in it. Continuous from one end to the other. Sunlight is like that. Incandescent light bulbs are like that. Some fluorescent light bulbs do that also. They produce a continuous spectrum. However, if you take individual elements and put them in a tube, a vacuum tube, and you inject the element in there, single element, and then you have electrodes in there to excite it, you add energy to it so that it emits light, they will invariably emit line spectra. Characteristic lines, and in this case, hydrogen we're using as our example because it's the simplest one, will produce characteristic lines and nothing else. Okay. I thought I replaced this one. One more second. Oh, that's the continuous spectrum. Okay. I left this this flash video slide there just because it had this picture that showed the passing light through a prism. In fact, that prism's turned the wrong direction to give us this spectrum. Anyway, you pass incandescent light through this slit and then through the prism, and it'll spread it out into its characteristic wave patterns. And these are continuous. That's refraction is what does that. Okay. I think this is a video to show line spectrum effects.
The discharge tube is filled with hydrogen gas. When a high-voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra, due to the appearance of bright lines. In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
So what's the significance of line spectra? Well, first of all, there should be you should see an immediate correlation between packets of energy versus discrete movements of electrons between the energy levels. Only certain energies are allowed for electrons in the hydrogen atom. That's what that line spectrum is indicating. It's pointing to that fact. It's not Niels Bohr's planetary model for the atom. Right? According to Niels Bohr, the planetary model says that the electron behaves like a planet. So theoretically, you can have it at any position around the atom. But this phenomenon says that no, you can't. Electrons can only occupy certain energy levels in the vicinity of a nucleus. And that energy is quantized. So this obvious question, what is it about hydrogen emission spectra that makes it not white? It's that quantized energy that says that you can only produce a certain number of wavelengths with the transitions of electrons between energy levels. If the energy levels were not quantized, then exciting hydrogen, you'd see white. In fact, every element, you could see white light. All possible colors would be emitted. That's what white light is. Okay. And there are regions between those energy levels where we say there's zero probability of finding an electron there. As it turns out, we talked about this before. Heisenberg's uncertainty principle, or is that in this chapter? I think it's in this chapter. It says you can know, if you measure how fast a small object is moving, can't know where it is. Or if you know where it is, you don't know anything about its motion, right? Can't have them both at that level, that size. Okay, so we have to speak of electrons and where they are and what they're doing in terms of probabilities. All right. So here's the Bohr model, and I start. See, that's what happens when I teach several courses. I forget what I've talked about in this particular course. The Bohr model of the atom says that an electron, and this is confined to the hydrogen atom. The reason it's confined to the hydrogen atom is it's the simplest one, and you've only got one electron to deal with. When you start getting 2, 3, 4, 5 more electrons in the same space around an atom, then you get the electrons interacting. And that just messes everything up. So the Bohr model is only for single electron atoms. They can be hydrogen atoms or they can be ions of polyelectronic atoms that have been stripped of all their electrons but one. Okay. So Bohr took this into account. I mean, his planetary model maybe started out as continuous positions in orbit, but he soon realized with the information that was available with the photoelectric effect and this line spectra and all that stuff, that he would have to limit the position of electrons around the hydrogen atom. This electron could only occupy certain positions. But he still retained the analogy of planetary motion. So these orbits are circular. He treated electrons as if they were particles in orbit. Now, when we say ground state for the hydrogen atom is where the electron is at its lowest energy level, which means closest to the nucleus. Right? Think of it this way. High energy electrons that are still attached to an atom move further from the nucleus. Right? They're being pulled very strongly by the nucleus, so you got to add energy to get them out here. So the higher energy levels are further away from the nucleus. The lowest possible energy state is the ground state. Now for the hydrogen atom, that's at energy level 1. But for other atoms, ground state could be higher energy level because they've got all these other electrons underneath them. So those ground states could be a higher energy level. Okay. The video showed you energy on this axis, and it doesn't matter what's on this axis. So here's energy level 1, very close to the nucleus. This is distance from the nucleus also. Distance and energy correlate. And then the second energy level is quite a jump. Then the third, fourth, fifth, the further you go out, the closer the gaps to the energy levels. This only shows 3 of them. There's a fourth one from energy level 6 down to 2, gives you the violet. So this is only blue, green, and red. So the electron jumps, if it jumps from 5 down to 2, you get a blue light. Okay, I think that's like 450 or something. Okay, yeah, the fourth emission line is missing. In this diagram, the nucleus is right down in here in the center, and this is the first energy level. This is the second energy level. So that's the Bohr model of the atom. Niels Bohr, he was a Danish physicist in the same time period as Einstein and several other giants of theoretical physics. Okay, we're missing the violet, so it would be 410 nanometers, jumping from 6 to 2. Right? We don't have 6 here, but if we did, it would be that wavelength. Okay, so here's the equation that Bohr used to describe the energy of an electron jumping from one level to the other. Right? This energy can be calculated, and here's our proportionality constant. Right? The real thinking part of this equation was deriving the relationship between energy is proportional to the Z, which is the number of protons, divided by the energy level squared. So for our hydrogen atom, this will be 1. So many times you'll see this equation written as this constant, and there'll be a 1 here divided by n squared. That's the energy level number, the principal quantum number. Let's see. Principal quantum number is n. That speaks to the energy levels. Okay. If this is the energy of the electron at a given energy level, and you calculate the energy at a different level, if it's a higher level, and when it moves from the higher level to this one, right, you just subtract the energy of this one from the higher energy level, and you find out how much energy was given off in that transition. And then that energy can be equated using Planck's equation. Once you know that energy from the transition, and that would be a delta E, that transition, then you can say, you can calculate the frequency or the wavelength, right? If we did like this, then you can calculate the wavelength and relate it to that to see if they're equal, right? To see if Planck's energy for the wavelength of light corresponds to the energy of transition for the electron. And I think that's what this slide is going to do. But it just gives you more definition. Here we go. This is what it would look like for the hydrogen atom. And notice this value has a negative. The more negative the number, the closer it is to the nucleus. And if you add energy to it, then you decrease the negative number until you get to a point where it's 0. You're at infinity then. And that electron has been ejected. Okay. So here we would have, this is the, and like I've said before, when you calculate a delta in any measurement system, it's the final condition minus the initial condition. So the final condition would be this one for the energy level, and this would be the initial condition subtracted from it, and you would get a change in energy. Okay, and we can contract this into a form that's a little easier to handle. So there's your constant, and there this term and this term. So we would subtract the initial values here from the final values multiplied by the constant, and that would give you a certain amount of energy, depending on whether it was negative or positive. And I'm pretty sure that if it's positive, then we've added energy too. So that is, it would absorb light energy. And if it were negative, it would be emitting light energy from an electron transition. Okay, now you can use this equation for polyatomic, polyelectronic atoms if there's only one electron. Okay, that's conditional. This only works for a single electron, hydrogen or ions. So if you had sodium, no, that's not a good example. If you had helium, if you kicked off one electron, then you would have one electron left, and then you could treat it like this. So that would be 2, 2, and this would be your energy levels. And there's some problems in there to use this calculation. Okay, so for a hydrogen atom transition, electron transition from 5 to 2, we should get blue light. That's what we observe. Okay. So if we say this transition is from 5 to 2, right? This is the final, this is the initial, this is the amount of energy that will be emitted, right? So it's negative, and the energy is leaving the atom. Then we compare that to calculating energy based upon Planck's equation, and we get this amount of energy, which is pretty close to that amount numerically. So we find agreement between these two, and that sort of is mathematical confirmation of the quantized nature of energy transfers, energy transitions inside the electron cloud around the atom. Okay. So the Bohr model fits very well with hydrogen atoms, or with hydrogen-like atoms with only one electron. Okay. But the model only works for hydrogen and hydrogen-like atoms. And the other thing that's wrong with the Bohr model is there's an assumption that electrons move around the nucleus in circular orbits. Right? If that were true, then when an electron gives up energy, as a matter of fact, a body that's orbiting some mass here is changing direction as it moves, right? Which means it is accelerating. In fact, it has centripetal acceleration. Its acceleration can be measured in terms of its movement toward the center. So when things accelerate, they bleed off energy. So these objects around in this circular orbit would bleed off energy, and eventually the electron would crash into the nucleus. But it doesn't. So we know that that is one indicator that the Bohr model is faulty, because it doesn't take into account that loss of momentum from acceleration. Okay, we can do all these calculations, right? And that should give us each of these wavelengths for those transitions based upon the Bohr model and his equation that described it. All right. Oh, here's Heisenberg. It was in here somewhere. So what Heisenberg said, he was another giant in the beginning of the 20th century, said that at this level, this equation, and this is just one form of his equation, it's the simplest to understand, is dependent upon x, which is the position, right? If you can locate your object and you can determine its momentum, mass times velocity, that is the v, that's the velocity. Then if the mass is very, very, very small, if the mass is very, very small, and the mass doesn't change, right? If you're locating something here and then here and then here, and it's the same object, that's why we say you can't know the position and the velocity at the same time. If the product of these two values is greater than Planck's constant divided by 4 pi, then those are the only conditions under which you can know both, is when they are greater than this value. So if your mass is huge, like my body, then yeah, we can find out where I am. But if my mass is very, 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 very small, then the uncertainty of this value is very large. Because if this product is going to be equal to that, or in the neighborhood of that, then if one gets big, the other one has to get small. So the uncertainty here is very small for a large mass, but for a small mass, the uncertainty is huge. Okay. Let's see. These were some other folks that we talked about Planck and Einstein. These others will come up. Some of them will come up. De Broglie is associated. We're going to associate de Broglie with the wavelength of a large mass. Like you can calculate my wavelength at a given speed. Like if I'm traveling 90% of the speed of light, then I'll have a given wavelength. Or if I'm traveling at half the speed of light, I'll have a different wavelength. That's where de Broglie comes in. It's called the de Broglie wave. Schrodinger, he developed wave functions that are applied to quantum mechanics, which we use to describe the structure of the atom. Right. You'll also remember, may have heard of Schrodinger and Schrodinger's cat, that thought problem. How do you know? If you've got a radioactive material inside a box, and when it decays, it triggers a poison that will kill the cat that's in the box with it. So how do you know? Well, based on that theory, the cat is both dead and alive at the same time. Okay, so that's where I think they call that superposition. And in fact, the technology that's being developed now called quantum computing. Quantum computers are supposed to be just massively head and shoulders above what we've got now. But it's very difficult to deal with them. And they're basing their work upon that superposition. One particle can be both a 0 and a 1 in a digital computer. If we could ever perfect it, then you could make codes unbreakable. In other words, hackers would never be able to figure them out. Okay. So we have to describe, since we can't know where the electron is, it's more important to know what's the energy of the electron. It's more important to know something about its momentum, its energy. So we describe its position in terms of probabilities. So these wave functions from Schrodinger describe the distance, the probability of finding an electron a certain distance from the nucleus. For this n equals 1, and this is, well, I'll describe what that is in a minute. But for this particular wave function, we see that the most probable location is very close to the nucleus. Now, this is a better representation because you're not going to have an electron right at the nucleus. It won't happen. It can't happen. So most of the electron density, the probability is going to be in this region here, and then it'll decrease out this way. Okay. Let me see. So I don't steal my own thunder. How are we doing on time? 12 o'clock. When am I supposed to stop? 1:20? Okay, I've been talking too long. I need to get on with it. We need to learn how to write the electronic structure of an atom. So, quantum mechanics was developed because of that Schrodinger problem, that Heisenberg problem. So we have to speak in terms of probabilities, and that's where the wave functions come in. We have to picture the electron not as an individual particle, but actually as a wave. The electron is a wave occupying a region of space around an atom. And one explanation I've seen that works pretty well for me is intuitively is, here's the nucleus. And the electron, if it's going to occupy this position, you've got to be able to fit waves in here like this for your electron that perfectly match. In other words, if the wave goes around here, it can't go around and then end up over here crossing itself like that. It's got to be a perfect number of wavelengths in that space. I think that's the thought process behind Schrodinger's equations. So we think of these orbitals in terms of the most likely place that you're going to find an electron. We can identify also places where you're definitely not going to find the electron. Those are called nodes. So let's look at quantum numbers. So these Schrodinger equations have built into them some variables. They have 4 variables in them. Right? The first variable is the principal quantum number. This principal quantum number, n, corresponds to Bohr's n in his equation. So there'll be 1, 2, 3, 4 on up, however many. And that's that, and there's no in between. It's either whole number 1, 2, 3, 4, as high as you need to go. And they refer to not only the energy of that region, but also the size. Because with that wave fitting in that space, it has to be, if you got more of them, it's got to be bigger. If you got more waves. So that's size and energy for the principal quantum number. The L number, the angular momentum quantum number, defines the shape of the orbital. Sometimes it's called the subshell. This would be the shell, this would be the subshell. And these quantum numbers, as we introduce them, are derived from the number before them. So we can derive L from 1, or we can derive L's, possible L's under 2, or possible L's under 3. So it's sort of a tree branching. And these can have values of from 0 to n minus 1. So if we have 4, it would go 0, 1, 2, 3. Okay. Then within these levels, that 0, 1, 2, or 3, any one of those, we have magnetic quantum number. So the angular momentum quantum number is sublevel of principal quantum number. Magnetic quantum number is a sublevel of any of the angular momentum quantum numbers. And they can have values of minus L in whole number increments up through plus L. So if you have a 3, you could have minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. And the magnetic quantum number addresses the issue of orientation in space. Which way is the orbital oriented? That's important for whether or not you will have proper orientation for a reaction to occur. Because when molecules approach each other, or atoms approach each other, if they're not positioned correctly, there won't be a reaction, no matter how much energy they've got. And then the last one is the electron spin quantum number. This can either be plus half or minus half. So within each one of these, you can have 2 electrons, one with a plus half spin and the other with minus half spin. Okay. So now let's see if we can use these values. Yeah, this is not very informative, but I will draw attention to this. These numbers, we keep them. When we are describing the electron structure of an atom, we keep the 1s and 2s, 3s, 4s for n. But it would get jumbled up pretty quick if we use the numbers for L, 0, 1, 0, 1, 2, 3. Now, those are the numbers that go into Schrodinger's equations. But when we write the electronic structure, it's more useful to assign letters to these. So 0s are S's, 1s are P's, 2s are Ds, 3s are Fs. If we had 4s, they'd be Gs. S, P, D, and F. That's enough, in fact, to get the whole periodic table. So that's why you'll see the structure of an atom written, I don't know, for example, 2P3, something like that. We use the letters because it can get confusing pretty quick if you use nothing but numbers. Okay. So let's do some examples. I think it'll be more instructive that way. For principal quantum number level n, so if n equals 3, I need to stand on this side so I don't block my own work. If n equals 3, how many subshells or different L's can be expected here? Right. How many L's can we have? We can have 0, 1, and 2. That's it. That's all the L's you can get from n equals 3. If you go up to a higher level, you can get more L's. There you go. All right. Oh. Give the designation of each. Oh, okay. That's true. The zeros are going to be S's, so it'll be 3S, 3P, 3D. Those are the possibilities you can have at this level. You can't have a free F. There's no such thing. You got to have a level 4 before you can get an F. Or a 2 can only have S's and P's. Right? Can't have D's. So for L equals 2, what's the magnetic quantum numbers? -2, -1, 0, +1, +2. Okay. So that gives you 5 orbitals for L equals 2. You have 5 orbitals. All right, so if we're talking about S's, which refer to the shape of an orbital, all the S's are spherical. If you just look from the outside, they would look like this. But if you slice them in half, they would look like this, where you're talking about electron densities here. For the 1s, it's virtually spherical, a solid sphere, with some differences in density there. With 2s, you've still got a sphere, but you've also got an internal structure where you have a region where there's no probability of finding electrons at all. That's a node. So when you get to the second level S, you get one node, and this is what it looks like in this diagram. So 1s would be like that, 2s would be like this, no probability, and then it jumps back up a little bit and then goes down. 3s, you get 2 nodes. Okay? So for P's, the shape is kind of dumbbell-like. You get this, and you get a plus side and a negative side. And this is a scatter plot for the P's. This is more accurate, actually. But this is easier to grasp visually. Okay? For the D's, it gets even more complex. You can have 5 different D's, but D is a 2, -2, -1, 0, +1, +2. So you have 5 possibilities. Whereas with the P's, you only have 3 possibilities because P is a 1, -1, 0, +1. So you can only have 3 possibilities in the P's. But the D's can have 5, and the F's, which are 3s, right? L equals 3. You can have M sub L's of -3, -2, -1, 0, +1, +2, +3, which would be 7. And then these are the shapes. Actually, they're, excuse me, orientations. The shapes, yes, they're different, right? Some of them, they have these donuts around them. But the orientation is different also. We're not going to deal with any of those. That's just way too much. This is not that advanced chemistry. I mean, they teach whole semesters of this stuff, and it's nothing but that stuff if you are a chemistry major. Okay, so then the last one is electron spin. So in any one of those, say, we have three p orbitals, any one of those can have 2 electrons. Plus 1 half, minus 1 half. And that brings us to various rules and principles that we need to observe when we're building atoms and their electronic structure. The first one is Pauli exclusion principle. This physicist, chemist physicist, said that in any given atom, when you're drawing this electronic structure, no 2 electrons can have the same set of 4 quantum numbers. They can have the same N, L, M sub L's, but they have to have opposite spin. So that would be the extreme. They would be next door neighbors, actually, if that were the case. That's the Pauli exclusion principle. The problem arises when we get more than 1 electron in there. Since we cannot predict the pathways of these electrons, then we don't know how they repel one another. We cannot calculate it. It's just impossible. So when we put electrons in there, as we're building atoms, we're adding protons, we have to add an electron for each proton. As we're building atoms through the periodic table, we have an order of addition, and we always add electrons as we move, lowest energy level first, and then we move up in energy level as we go. And that's based primarily upon principal energy levels, like that, moving this way, and then subshells, right? That's all you can have for this one. This one could be that one, and it could be this one. This one could be that one, or this one, higher energy level as you move across. Now, there are going to be some switchbacks in here. In fact, I'll just give you a heads up. We actually, in order of energy, we get to 4s before we get to 3d. Okay, I'll show you how that works in a few minutes. All right. I left this flash in here to illustrate that energy levels shift as you add more electrons and protons. Those, we might expect them to be 1s, 2s, 2p, 3s, 3p, 3d, 4s, in that order as we move up. But in fact, when you get more electrons in there, these shift to put the 3d above the 4s. Right. And this is based upon mathematical calculations. Right. And then confirmation by observations. So if this thing worked, then as you add electrons, you would see these shift upwards, but this one eventually would be higher energy level than 4s. Okay. I get the feeling that this one's kind of out of order. Penetration effect. I'll just describe it and squirrel it away in the back of your head until the rest of the chapter is finished, and then maybe it'll make sense. The penetration effect we're trying to describe here is in terms of probability of finding electrons closer to the nucleus than you would expect. And the penetration effect contributes to that shift in energy levels when you start adding more electrons, right? So the penetration effect of the three Ds, is such that more electron density is closer to the nucleus than the four S's when you get to that point. Excuse me, the four S's penetrate more than the Ds. Yeah. We would expect 4S to be higher energy than 3Ds, but now it's lower energy because of that penetration effect. Okay, so let's see what it looks like. If we're just comparing the S's and the P's of the same energy level, this is one description of the penetration effect. The distance from the nucleus plotted against probability of finding electrons there for the p orbital is constant. I mean, it's increasing here and then it decreases like that at that distance. Whereas the 2s has most of its concentrations out here, but remember the 2s has one node. So this node occurs here, and then you get some electron density here. So taken all together, that makes 2s a lower energy than 2p. If we look at 3s, then you're going to get two nodes, and you get significant penetration here from the 3s at this distance from the nucleus. So it's like it's busy traffic around the nucleus with all these electrons. Okay, so let's look at, we looked at 2s and 2p. We couldn't look at 2d because it doesn't exist. So let's go to 3s. 3s is here. Let's look at d. The 3d is like this with no nodes. The 3p has one node here, right? So it penetrates deeper than the 3d. And the 3s penetrates even deeper. So that's why 3s, 3p, and 3d are in that order of energy. But this doesn't include 4s. 4s penetration would be below 3d. It would have a node and then a penetration down to less than 3d to give it that lower energy level. Okay, so with that as a preface, let's talk about the periodic table now. Periodic table was coming for quite a while. Eventually, in the late 18th, early 19th century, chemists, as they were coming to be called, I don't know if they were by this time, but they might have still been called alchemists. No, they were natural philosophers. That was the term that was used for scientists, natural philosophers. Johann Dobereiner was German, and he noticed similar behavior among some groups of elements. And with all the elements they knew at the time, they came in threes. So he called them triads. So there were several triads that he had identified. Most notable was the halogens, chlorine, bromine, and iodine. They have very similar behavior. Now, they don't have the same phase at standard temperature and pressure because chlorine's a gas, bromine's a liquid, and iodine's a solid. But they did have similar reactive characteristics. And there were several others. That's as far as he went with it, just developed those triads. Then along came a little bit later, this fellow, this German, Julius Meyer, and Dmitry Mendeleev. They more or less simultaneously conceived of a periodic arrangement of elements in a tabular form. So they published their work. And they took all the elements that they knew and put them in positions that they thought were characteristic, where you would group them according to their chemical behaviors. And Mendeleev also incorporated their known masses. At this time, they were just starting in the late 19th century, around 1860, in that range. They were just starting to get a handle on numbers using Avogadro's law. Right? Have I told you about that conference in Karlsruhe, Germany? Okay, yeah. So Mendeleev took advantage of that information that came out of Canizaro's publications. And he credited Canizaro with helping him figure out how to arrange things in his table. So they both published these tables. And originally Mendeleev's table had the groups going this way. So it'd be like fluorine, bromine, iodine, that way. But his second publication, he rotated them 90 degrees. Mendeleev is given the lion's share of credit for developing the periodic table for one reason. He made predictions. When he arranged elements in his periodic table, he noticed that if he went mass, next heaviest, next heaviest, next heaviest, he moves across here, and he arranged them like that and in groups. Then he noticed that if he put the next element, the next heaviest element in that group, it didn't match. It didn't have the same chemical behavior as that group. So he moved it over to the next one because it did behave like those. Said there's an empty spot there. And one day somebody's going to find an element and stick it in that place. And not only that, he said it's going to have these physical chemical characteristics, atomic weights, chemical behavior, whatever the case may be. Sure enough, they found it. That predictive ability of Mendeleev's periodic table is why he gets most of the credit. Okay, so the periodic table is arranged like this, and you've seen it before. And it's arranged in groups and periods. So the groups are vertical, right? And some of them behave fairly well in terms of their chemical behavior, their similar behaviors. Like the alkaline metals behave a certain way, the alkaline earths behave a certain way, the halogens behave a certain way. Of course, the noble gases don't behave at all. And then the chalcogens behave a certain way, and the nitrogen group, the pnictogens behave a certain way, carbon group, and you've got the boron group. Transition metals, they sort of group together because they're a little squirrelier with their chemical behavior. But so those groups exist. And then the horizontals are the periods. And they're called periods. My best analogy is periodic motion. Right? When you set a pendulum moving, it moves. Yeah, it moves. But it comes back to the same spot each time. It goes through a period and sweeps back same spot. That's the characteristic of periodic motion. It moves, but it comes back to the same place. So if you think of that horizontal, the rows, as periods, then if you stack them up like this, like that, the next one over here beyond neon is actually going to look like alkali metal. So you don't put it over here, you put it over there. So you've gone through here and you've got to backtrack. You've gone through here and you got to backtrack. That's your period. You're back to the same place you were before. Now, I mentioned some of these groups, halogens, these guys right here, transition elements. These lanthanides are called that based upon the first member of their group, lanthanum, which is right here. And then actinium is the first member of this group, which is right here. And the reason they're pulled out, well, actually for two reasons. We pull them out so that the periodic table doesn't have to be 10 feet wide. We just drag these out here and they're separate. Plus, the other thing, and I think it's on the next slide. Oh, I'll get to it in a second. Major divisions. Right. You have metals, non-metals here, and there's a zigzag that goes like this right here. And to the right is metals, to the left is non-metals, but there are a few in here that, depending on their environment, the chemical environment, they behave like metal, sometimes they behave like non-metals. So they're called metalloids. And which ones belong to that group is variable, depends on the publisher. Okay. Oh shoot. I had a roll going and now I just got stopped. Okay, let's go through some more rules and we'll get to the topic I was trying to hit here. So we've covered the Pauli principle, exclusion principle, right? No two electrons in an atom can have the same set of quantum numbers. Then we have the Aufbau principle, which I don't know German, but I looked it up and basically means do it this way. So the do it this way principle says that as we add protons, we add electrons in the next highest energy level. So we build it from low energy out. That means we have to know what those energy levels are, what order they occur. And I'm going to show you that in just a second. For instance, for oxygen, we would have them in this order. We have 1s would be the lowest energy, 2s would be the next, 2p would be the next. And s's can only have 2 electrons. So you have 2 there, 2 there. P's can have 6 because we have 3 m sub l's, right? Minus 1, 0, and plus 1. So you can have 2 electrons in each one of those. That's why P can have 6. And in oxygen's case, we only have 4. If you have 6, what do you get? 2 more electrons. 1, 2. You have neon. So if you have full orbitals, you have noble gases. Okay. That's the Aufbau principle. Hund's rule. Hund's rule talks about pairing of electrons, right? Plus 1/2, minus 1/2 spin. Hund's rule says when you're inside an L orbital, if you've got sublevels in there, like m sub l minus 1, 0, plus 1 for P's, right? If we have a P orbital here, and we have 3 sublevels, right? Minus 1, 0, and plus 1. When you start putting electrons into a p orbital, you can't pair them up until each one of these has 1 electron. So you would add them in like this, like this, like this. That's what I do, spin up. And then if you got another one, like oxygen, you'd have 4. Now you can start pairing them. That's Hund's rule. And these rules are developed to explain real phenomena. Right. Without those rules, then you would create an atom electronic structure that does not exist. It does not satisfy the observed conditions. Okay, so there's oxygen, for instance. And this is what the orbital diagram would look like. So let's take another one rather than oxygen. Let's build one. How about nitrogen? How about nitrogen? So nitrogen has 7 protons. 7 protons means a neutral nitrogen atom has 7 electrons. So we put them in order: 1s, 2s, 2p. That's probably all we're going to need. So we've got 2 there, 2 there. That means 4. We got 3 left over. So that would be the designation for nitrogen. And if you wanted to speak to individual electrons, then rather than use boxes, I like to just use lines. It's a lot quicker. So you'd have 2 here, 2 here, 1, 2, 3 there. Okay? Yes, ma'am. Thank you. It's all recorded. So does any of this look really strange to you, or have you seen it before? Oh, okay. Well, you're just, so you're just kind of brushing up. Okay.
And we had to draw them, so,
Did you have to draw them like this with boxes?
well, no, we didn't have to do the boxes, but we did have to do the arrows.
Okay.
And,
Yeah. Spin up, spin down. Yeah. Okay. So the concept of valence electrons. It's very simple. All the electrons that are at the same principal quantum number level in the outermost shell of the atom are valence electrons. So if we had, let's say magnesium. Right, magnesium was 12. So lowest energy, we start moving our way up. 2p, 3s, 3p. We'll stop there. That's probably enough. So we put 2 here, 2 here, right? That's 4. So we got 8 left. 6 there, right? And then we got 2 more, right? So we don't need 3p. So what are the valence electrons? Those 2 right there. So magnesium only has 2 valence electrons. That's why when we learn to write and name compounds, the second group, the alkaline earths, are always 2+. Because in order to be a 2+ ion, you get rid of 2 electrons. Just kick those 2 off. If you do that, what does it look like? It looks like a noble gas, doesn't it? Looks like neon. Okay, so those are valence electrons, and all noble gases have 8 valence electrons. At least the ones we're going to deal with. This is what I was headed at before. The structure of the periodic table. As we're filling those orbitals, we always fill the s orbitals for these alkali metals and alkaline earths. Those are always the s orbitals filling as you go from left to right. Right. So there's only 2 electrons in the s orbital, so you can only have 2 of those groups. When you get over here, you can have 6 of them because p's have -1, 0, +1, 2 electrons each, 6 electrons. So you can fill them from left to right, and you have 6. This group are the Ds. How many sublevels can D have? -2, +(-1), 0, +1, +2, 5, which means 10 electrons. So you should have 10 positions here. Okay, and Fs, you should have 14 because you can have 7 sublevels, M sub Ls, and 2 electrons each. So that's the other reason that we pull these out here, because we separate them out as f orbital filling. Transitions are d orbital filling. The representative elements are these and these, so they fill either s's or p's. Okay, so that's the structure of the table, and knowing that, you can write the electronic structure from the periodic table. Notice that as you're moving across the period here, this 3s, 3p's, 4s, and then when you get into this region, you have to back up to 3b's. That's what I was talking about earlier. 4s is lower energy than 3b. So we fill 4s first. Then we fill 3Ds. And then we get back to the 4Ps. And then 5S. Now we got to back up to 4D. Okay, so that's the way I use the periodic table to write the structures. And just a word of warning, there are some exceptions in here. Actually, over here and over here, you get some exceptions. This is the other way. Use the diagonal method. So if we write the 1S, that's all at the one level can have it. S is it. Right? Because one can have L's of starting with 0. Oh, that's it. You only have one of them. Right? 2s can have a 0 and 1. Right? So an S and a P. 3s can have an S, a P, and a D. So you can have as many as you have a principal quantum number. So 4 can have 4 levels. 5 can have 5. We could go out to G here if we needed it, but we don't know enough elements to do that. So we stop at S. And we write them in here as the principal quantum number and the level, sublevels. Then we go up here and do our diagonal, right? 45-degree diagonal, 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S. So that's the other way you can do it without using the periodic table. But I prefer the periodic table, to be honest with you. But this does correlate to the proper sequence of energy levels. Okay, let's take examples. Sulfur. See how many protons does sulfur have? 14. No, that's sulfur. 16. So sulfur has 16. So we start 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P. Maybe that's enough. Let's see. And we start filling them in. 2 here, 6 here. 2 here, 6 there. So that would be, let's see, that would be 10. Okay. Oh, that's 18. Too many. So what's that for? Let's see. 2, 4, 10, 16. So that would be sulfur. Now we've got a shorthand also. If you look at the atom's electronic structure in terms of core versus outer layer, I was going to say valence, but that's not necessarily true. Core versus outer layers. Then if you take sulfur and you go backwards on that period, and then you come back up to this period, neon. So if we say neon has 10, then what's beyond neon? Okay, neon is here. So beyond neon is 3S2, 3P4. That's even a shorthand for writing the electronic structure. And it gives you the information you need, right? Because these are the ones that are going to be actively involved in chemical reactions. How about barium? Barium, I don't want to write the whole thing for barium because look where it is. What is it? 56 electrons. That'll take us all day. Let's see. Okay, there's sulfur. Barium, if we use the shorthand method, we'd say barium is here. So we go back up to the next level to the neon gas xenon at 54. Xenon 54. Right? And then barium is in what period? Is that 6? Yeah, 6. Barium is filling the s orbital, 6s2. That's it. And this one is europium. So europium is down here, I think. It's lanthanide. So we would back up until we get to xenon, and then we'd work our way through. Right? We'd have to go through barium, and then we have to go through lanthanum and on down to F7, 4F7. Notice that the D's are one less principal quantum number than the period they're in. So these are all 3 Ds. And the F's are 2 less. So if this is 6, then this is going to be 4F. If this is 7, this is going to be 5F. Okay. All right. So let's look at some periodic trends of the table. There are several of them, but we're going to focus on these 3: ionization energy, electron affinity, and atomic radius. And these are generalized trends. They're not absolute, and you're going to get lots of variability, especially when you try to move through the transitions. They kind of have a double hump there. But if we fix our attention on the representative elements, then the trends tend to match a little better. Oh yeah, you'll need one of those. Each one. Yeah, it's thick. I didn't want to disappoint you guys, so I made them thick. Okay, ionization energy. What do we mean by ionization energy? How much energy does it take to kick off one electron from the atom? In this case, we're starting from a neutral atom. But the phase is very important. The phase has to be a gas. The reason being, if we started from a solid, say it's a metal, we started from a solid, you're going to have to put a lot of energy in there to make it a liquid, and then a lot more energy to make it a gas before you get anywhere near kicking off an electron. So it always has to start with a gas. Okay? And the amount of energy required to produce this one ion with a free electron. Now that's for the neutral atom. You can take this one and do a second ionization energy, like we did with magnesium. So magnesium, here's the first ionization energy, here's the second one. Kick off another electron, and the third one, kick off a third electron. Okay? And notice that when we do that, the first one takes a certain amount of energy. The second one takes a little bit more. Okay? Because you're trying to remove a negative from an already positive ion, which takes a lot more energy. But when we get to the third one, now what's happening? When we get rid of these first 2 electrons, what does magnesium 2+ look like? Looks like a noble gas. Noble gases hang on to their electrons with much tenacity. So the third electron from magnesium is going to take a whopping amount of energy to get off there. So when you get down, we call that the core. When you get down into the core, you're going to expend a lot of energy to get that electron out. And that's true for any of these. If you have, say, sodium, it's going to take a certain amount of energy to get rid of that one electron from sodium. But now, with one electron gone, sodium looks like a noble gas. So the second ionization energy is going to be high for sodium. Whereas magnesium was an alkaline earth, it can afford to give up 2 valence electrons before it gets into the core. And aluminum, you would be able to get 3 out before you get into the core. Okay? All right. So as we go across a period, the ionization energy from left to right tends to increase. And there's a very simple explanation for that. You're adding electrons to the same energy level as you go across the period, right? Like 2s, 3, 4s. But you're also cramming more protons in the nucleus. You're increasing the effective nuclear charge. which makes it more difficult to remove an electron. That's across a period. As you go down in a group, the ionization energy decreases because those electrons are being added from one to the next in the group. They're being added to outer energy levels. And the electrons in the core are shielding those outer layers from that positive charge. So you decrease going down, increase going to the right. Or conversely, you increase going up a group. So put those two together, up and to the right. So lower left, upper right, you increase ionization energy. Let's see. I already gave you that explanation. We do notice, let's focus on these first. The noble gases. So helium, neon, you're going down in that group. So the ionization energy decreases as you're adding electrons to outer shells. That follows the trend. Halogens, fluorine, chlorine, where's bromine? Bromine, where's iodine? Well, they don't mark iodine. It's probably right here. So that decreases. But you do get to the place, if we go across a period, left to right, we're going to go, let's see, lithium, beryllium, boron, nitrogen, oxygen, fluorine, across that second period. Notice that it's not uniform from left to right. Right? You increase from left to right until you get to go from beryllium to boron. Or you go from nitrogen to oxygen. So what are we dealing with there? And you see that several places, right? And they always occur in similar locations in the periods. So for beryllium to boron, you're moving from S to P plus, well, and the P's are generally a little bit higher energy level. Right? So you're further from the nucleus, even though you've got another proton, you're a little bit further from the nucleus, which makes it easier to remove that electron. That's from beryllium to boron. From nitrogen to oxygen is a little more complicated. From nitrogen to oxygen, you're going from, let's see, yeah, 2p3 to 2p4. So let's just focus on nitrogen and oxygen. So here you've got 2p, you get 2p. And this one's only got 3 electrons in the p orbital. This one's got 4. Okay. Now, the electron repulsion here is obvious. Right? You got these two with opposite spins in that sublevel, whereas these have their own sublevels. So these two are going to experience more repulsion. That means one of them is going to be easy to get rid of. So as we're moving from left to right, we expect the ionization energy increase, except for oxygen, you get this electron. So the first ionization energy is going to dip down below nitrogen before it starts back up again. Okay. Which one of these requires more energy to remove an electron? Well, just look at their position in the chart. Sodium, they're in the same period. Sodium's way over there, chlorine's way over here. It takes more to remove chlorine. How about this one? Lithium and cesium are in the same group. Cesium is way down at the bottom, lithium is way up at the top. So lithium should take more energy to remove an electron. Higher ionization energy. How about second ionization energy? Lithium versus beryllium. Second ionization energy. So lithium, when you remove one electron, you're down in the core. Whereas beryllium, you've got a couple of electrons to deal with, don't you? Yeah. It's like sodium and magnesium before. So the second ionization energy is going to be much higher for lithium. And this just illustrates, depending on how many valence electrons you have, sodium has 1. So by the time you get to the second one, you're in the core. Magnesium has 2, so you have to go to the third. Aluminum has 3, you got to go to the fourth one, and so forth and so on. Okay, electron affinity. The mistake that we're tempted to make is to say electron affinity is just the converse of ionization energy, but it's not. We're starting from the same place, right? Neutral atom. We want to know how much energy is given up when the electron is captured by that neutral atom. When it becomes a negative ion, we should get some energy back because that electron is out here at infinity and it drops down to an energy level around the atom. It has to give up energy. Right? So the value is going to be negative. Right? So the more negative the number, the higher the electron affinity. That's one of the keys that kind of twist your head around sideways. The higher the negative number, the higher the affinity. So, and again, we have to have a gas. Right? We can't be dealing with any phase changes here. We've got to eliminate those phase. We got to deal with phase changes some other way. So as you go, that could be, yeah, because the strength of attraction for an electron determines how likely it is to form that ion. So what are the trends? From left to right, the electron affinities become more negative, which means a stronger attraction. So fluorine would have a stronger attraction than, I don't know, who's in that group? Lithium? Yeah. Fluorine would have a much stronger attraction, a more negative value, right? Because these are all quantitative values. These electron affinities, ionization energies, they're quantitative. So this value for fluorine is going to be much more negative than for lithium. And then the other trend, becomes more positive going down a group or more negative coming up a group. And that's simply because the electron is being attracted to non-shielded protons for the smaller, higher atoms in that group. So there you have the same trend. Lower left to upper right, the electron affinity increases, but the value itself becomes more negative. Okay. Atomic radius. All right. This is kind of a difficult concept to convey because how do you measure the radius of an atom? You got to know where it stops, don't you? Where's the outer limit of the atom, right? This is an electron cloud that's defined in terms of probability. So where's the limit? We don't know exactly. So you have to measure it in terms of how it interacts with other atoms. And then once you can find the distance, you can measure the distance between nuclei of two adjacent atoms, then you just take half, and that's roughly the atomic radius for that atom. But it depends on what kind of atom it is. Right? Two types are recognized. One are metallics, metallic radius, and that just involves like packing marbles. How do the marbles pack? And we deal with that the first couple of chapters in 102. We'll get into that detail. But for now, they're packed in there a certain way, and we can determine this distance here using X-ray diffraction. And that has to wait till 102 also. But once you know that distance between them, you just take half of it. That's the metallic radius. The covalent radius, you have to deal with not just solids, but you have to deal with gases and liquids. And usually it's determined for gas, for the gas, covalent. So it's half the distance between a homonuclear diatomic molecule. And for this one, you can use several different types of methodology. If you can get it into a regular crystalline structure, so you can make a solid out of it, then you can use X-ray diffraction. Sometimes you have to fire electrons at it to see how they behave. Or sometimes neutrons are fired at it. So all of these can have wave characteristics, right? Well, that's definitely a wave because it's light. But this electron has wave character, neutrons have wave character. You can use microwaves or a combination of them. And it's really a detective game to figure out what is the radius. And you'll find different values depending on the authors. Okay, so what's the general trend? Well, if we use values from one author, don't try to mix them up too much, then we would say that the trend is across a period from left to right, the atomic radius decreases, gets smaller. And that's primarily due to increasing effective nuclear charge. You're adding more protons, so you're shrinking the electrons down, closer to the nucleus. And they're all in the same energy level, right? So that makes sense, shrinking them down. You're not trying to occupy a higher energy level to shrink those. You're only in that same energy level as you add electrons, so they shrink with more positive charge. As you go, let's see, down in a group, the orbital size generally increases. That's because you're adding electrons to higher quantum levels. You're just making them bigger. And you're not increasing the effective nuclear charge that much because the core electrons are shielding the outer electrons. So the trend for atomic radius is increasing from upper right to lower left. And this is what they would look like. These are only the representative elements. So these are the s orbital filling and these are the p orbital filling. And they tend to follow the trend fairly well, especially up here in the lower principal numbers. Okay, which would be larger, sodium or chlorine? Sodium, yep. How about lithium and cesium? Right, they're in the same group. Cesium's down here. That'll be bigger. Now, what happens to these atoms when you start making ions out of them? Well, the metals tend to lose electrons. So they're going to get smaller than their neutral atoms. But the nonmetals tend to gain electrons, most often. So they tend to, like that. So when you see a model representation of sodium chloride salt, you'll see the sodiums are like this, and the chlorides are like that. Simply because lost electron, gained electron. And that has bearing on how they pack together too in that structure. How about this in terms of just looking at the orbitals themselves? The 1s orbital for hydrogen versus the 1s orbital for lithium. Which one would be larger? Hydrogen. It's just the 1s orbital, not the whole thing, just the 1s orbital. You've got more protons in lithium. It's shrinking the electrons that are occupying that 1s orbital. So lithium is going to have the smaller, and hydrogen will have the larger. How about which one's lower in energy? the 1s orbital is lower than energy. Well, the smaller one is closer to the nucleus, so it's lower energy. So even though they're both designated 1s, there is a difference in the energy. The lithium would have the lower energy 1s orbital. Okay. All right, still got time, but let's see. Yeah, we're good. Okay, we'll make it. How about arranging these elements according to what? First, ionization energy, increasing ionization energy, right? Lower left to upper right or across. Oxygen, fluorine, and sulfur, how are they arranged? Oxygen, fluorine, okay. Sulfur is below oxygen. So below and to the left, it's the lowest. So it should be sulfur, oxygen, fluorine, increasing. Sulfur, oxygen, fluorine, increasing. Atomic radius is just the other way around, isn't it? So it should be fluorine, oxygen, sulfur, increasing radius. Okay. Oh, we are close to the end. Final thoughts. So what determines the chemistry of atoms? The valence electrons. They're the ones that are the least attracted compared to the core electrons. They're the ones that are out here too, right? When two atoms approach, what do they see first? They see the outermost electrons, right? That's where the business happens. We can determine the electron configurations from the periodic table, with some exceptions. We didn't talk about the exceptions yet. Maybe when we get into working some problems, we'll look at exceptions. Certain groups in the periodic table have special names. Those are historical significance. Basic division of the elements in the periodic table, metals and nonmetals. And they have, they're from different worlds.